In this video, we look at one of the most important physical properties of atoms, atomic mass. We also learn how to calculate the mass of molecules, known as the molecular mass, and also the mass of ionic compounds, known as the formula mass. When we talk about atomic mass, what we're really talking about is relative atomic mass, and we need to talk about it on a relative scale because we know that the masses of atoms are actually very, very small. For example, the hydrogen atom has a mass of 1.674 times 10 to the minus 27 kilograms. And even the most massive naturally occurring atom, the uranium atom, has a mass of 3.953 times 10 to the minus 25 kilograms. These are very, very small numbers to use for mass and not very convenient in chemical calculations. The standard SI unit for mass is the kilogram, which is defined by the International Prototype Kilogram, which is a cylindrical piece of platinum iridium alloy that is kept in a sealed vault just outside of Paris in France. The mass of this cylinder is defined as exactly 1 kilogram. Unfortunately, the masses of atoms, molecules, and ions are too small for this kilogram mass scale to be conveniently used, and what we need is another piece of matter against which the masses of atoms could be measured against in a relative sense. And the piece of matter that's been chosen is the carbon-12 isotope of carbon. Now we know that a carbon-12 isotope has exactly 6 protons, 6 neutrons, and 6 electrons, so its mass can be very precisely defined. One carbon-12 atom is defined as having exactly 12 units of mass, and we say that one atom of carbon-12 is equivalent to 12 atomic mass units. Atomic mass units are often abbreviated to AMU, or they take on the Greek symbol mu. Now the mass of a carbon-12 atom is, as we've said, 12 atomic mass units, and this is an exact number, so for all intents and purposes, this value has an infinite number of significant figures. The actual mass in kilograms of a carbon-12 atom is 1.99265 by 10 to the minus 26 kilograms. And if we divide that number by 12, we can see that one atomic mass unit is equivalent to 1.66054 by 10 to the minus 27 kilograms. And that is worth knowing from an academic point of view, but in practice, we rarely ever use this relationship. What we'll actually use is the knowledge that a carbon-12 isotope has a mass of 12 atomic mass units and that every other element in the periodic table has been assigned a mass that has been measured relative to this value. And so we can see that these numbers under the chemical symbols in the periodic table now start to take on some meaning. The number under the element in the periodic table is referred to as the atomic mass, and as we've just noted, the units are expressed as atomic mass units. In reality, however, it should be called the relative atomic mass because that mass is actually relative to the mass of a carbon-12 atom, which we have assigned as having a mass of exactly 12 atomic mass units. So we can look at the periodic table and pick any element in the periodic table, for example, hydrogen at number 1, and we can look at the number underneath the symbol, 1.00794. And we can say that the atomic mass of hydrogen is 1.00794 atomic mass units. So roughly speaking, a hydrogen atom is 1/12 as massive as a carbon-12 atom. We can look at another element, magnesium for example, and we can see that its atomic mass is 24.3050 atomic mass units. And roughly speaking, a magnesium atom is twice as massive as the 12 atomic mass units for a carbon-12 atom. Now, if we look at number 6 on the periodic table, carbon, we see that it has an atomic mass of 12.0107 atomic mass units. It's not exactly 12. An atomic mass of exactly 12 is the atomic mass for a carbon-12 isotope, which constitutes about 98.9% of all carbon atoms in a carbon sample. But carbon samples actually contain carbon-13 isotopes. About 1% of all carbon atoms are carbon-13 atoms. And they also contain carbon-14 atoms, and about 0.1% of all carbon atoms are carbon-14. This means that the average mass of a carbon atom, when the relative abundances of all isotopes are taken into account, is slightly above that of carbon-12. And this is why we get a mass of 12.0107 atomic mass units instead of exactly 12. Because the atomic mass values, or more correctly, the relative atomic mass values that we see in the periodic table represent the average mass of all the available isotopes, when their relative abundances are taken into account. We now turn our attention to the mass or relative mass of molecules, which we refer to as molecular mass. The way we calculate the mass of a molecule is to simply sum the atomic masses of all the atoms in the molecular formula. We can use the molecular formula for water as an example. In this molecular formula, we recognize that H2O has 2 hydrogen atoms associated with it. We can look up hydrogen in the periodic table at number 1, and we see that again its atomic mass is 1.00794 atomic mass units. So the contribution from those 2 hydrogen atoms is 2 times 1.00794. We can also see that water has only 1 oxygen atom. We look up oxygen on the periodic table and note an atomic mass of 15.9994 atomic mass units. So the contribution from oxygen to the overall molecular mass of water is 1 times 15.9994 atomic mass units. We can sum these values, 2 times the mass of hydrogen plus 1 times the mass of oxygen, and we get 18.015 atomic mass units. And the molecular mass for any molecular formula can be calculated in exactly the same way, simply by adding up all of the atomic masses of all of the atoms represented in the molecular formula. For ionic compounds, it's slightly different. There are no molecules, and so what we actually refer to is a formula mass. But again, we simply add up all of the atomic masses of all of the atoms in the formula unit for ionic compounds. So, for an ionic compound such as calcium phosphate, represented here by its formula unit, Ca3PO42, we can see that there are 3 calcium atoms in the formula unit. We can look up calcium in the periodic table, number 20, and we can see its atomic mass or relative atomic mass is 40.078 atomic mass units. So the contribution from those 3 calcium atoms to the overall formula mass will be 3 times 40.078 atomic mass units. We can also see in the formula unit that there is a single phosphorus atom inside the brackets, and we also recognize that there is a subscript 2 outside the bracket. So in total we have 2 phosphorus atoms represented in the formula unit. We can look up phosphorus on the periodic table, number 15, and see that its atomic mass is 30.9738 atomic mass units. And the contribution from phosphorus to the overall formula mass of calcium phosphate will be 2 times that number. Finally, we can see that there are 4 oxygen atoms inside the brackets, but the 2 outside the brackets means that we have a total of 8 oxygen atoms in this formula unit. We can look up oxygen in the periodic table, number 8, and we see that its atomic mass is 15.9994 atomic mass units. The contribution from oxygen to the overall formula mass is therefore 8 times that number. We can now sum all of these values, 3 times the atomic mass of calcium, plus 2 times the atomic mass of phosphorus, plus 8 times the atomic mass of oxygen, and we get the value 310.177 atomic mass units. And again, the formula mass for any ionic compound can be calculated in the same way, simply by summing up all of the atomic masses of all the atoms in the formula unit. So in conclusion, the number under the chemical symbol in the periodic table now has a new and significant meaning for us: the atomic mass or relative atomic mass. And using these atomic mass values, we can calculate the molecular mass, the mass of molecules and molecular compounds, and we can calculate the formula mass, the mass of ionic compounds.